Hello. In this tutorial, we're going to be discussing how to manage advanced data structures. In particular, we're going to look at how to modify our linked list class that we defined so that we don't have to define a separate class for a linked list of integers versus a linked list of candy bars versus a linked list of strings and so forth, so we can have generic or templatized classes. And then we're going to talk about how to modify our linked list so that it can point in both directions. So it's a doubly linked list. And finally, we'll finish off with a discussion of how to define a recursive linked list. Same functionality, just a slightly different implementation using recursion to achieve that data structure. I've already coded all of this up, so we're just going to go through and look at each one of these individual parts. And up until now, if we wanted a linked list, we had to say something like list data is equal to a new list, and we could put a new candy bar into that with some information. And if we wanted a different type of list to hold a different type of information, I'd have to say list int data2 is equal to a new list int. Let's say I wanted this list to hold integers, and I could do something to this effect. So I would have to actually have separate classes to hold the different types of information. And in reality, the list shouldn't care what it holds. So can we not construct something called a generic list that's going to hold different types of things depending on what I tell it? Now the syntax for using this is going to look like so. I've got the class name here. I'm calling this generic list, and it's based off of my list class. But notice I have this less than, greater than brackets, and I'm specifying the type of thing that I want to hold here in those less than, greater than brackets. Now generic list then isn't just a class by itself. It has to be a generic list of a particular type. So data, the object data, is actually an object of the generic list on candy bar class. And then I can insert candy bars into this data object because data is designed to hold candy bars. Now down here, I can use the same generic list class and insert integers instead. So data2 is an object of the generic list on integer, and I'll be inserting integer values into this data2 object. So the same class, generic list, can hold candy bars or integers or really any data type that you want to have it hold. Now let's look at how to pull this off in implementation. Notice here that I've added this less than, greater than bracket symbol with a T, and T could be anything. You could put the word Bob here. T is going to be a marker indicating the data type that I want this class to hold. So now, instead of a class node that has data of type int or candy bar, I'm going to define this private class node that also takes in something of type T, and the data portion is going to be of type T. And the next is going to be a node, is going to be a reference to a node that holds T. So you can see that instead of specifying anywhere that I would have had integer or candy bar, I'm going to list this special marker T. And again, you could call this Bob, or you could call this data type, whatever you want to call it. Just be consistent in defining it in the class at the top of the class here, and then using it throughout the implementation of the class. Okay, so here's our private class node that's going to be internal into the generic list, and I'm going to manage data of type T. Notice here my insert now, I haven't changed any of this code, but the only thing I need to change is instead of this being an insert, the value being of type int or a candy bar, it's just of type T. The insert to end also has something of type T coming in as a parameter, and none of the code here has changed. We have the toString function, which hasn't changed, the length function that hasn't changed, the position of I'm looking for something of type T, and when I find it, right, when I say current.data.equals this value to find, then it's going to return the index of. If I'm doing a deletion, I can take in something of type T that I'll call toDelete, and if the thing that I'm looking for is a match here with the data, then I'm going to move the pointers so that it bypasses it and actually deletes it. So this is a simplified version of our list function, or list class. We now no longer are using some of the methods that we had previously defined, but I needed to remove those to make it truly generic. I can't look at the caloric count or matching on the name because those getName and setName and getCalories methods aren't defined. I just have this generic T, and I can use my equals to see, is this the one that you want to delete? The important thing to see here is that I can make my collection class that I've defined to be generic enough to hold anything, and I can use this special less than greater than bracket to mark this type, and throughout the code I'm going to use that type to indicate filling in values and searching for values and so forth. Okay, let's go ahead and run this then. You can look inside of main and you see that I have created a generic list of candy bar I'll call data, and I'm going to insert the Snickers, Milky Way, Almond Joy, Zagnut, Almond Joy, and Super Snickers. This is nearly identical to the code that we've used in previous tutorials, and just print out the list as we go. You'll also notice that I'm using the same, so this is generic class, I'm using the same generic list class. This time I'm passing it integer, and for the object data2, I can then insert the values 42 and 9 and 13 and so forth. So if we run this, you'll see that the output is I can use my generic list to hold objects of the candy bar type, and I can also use, this is data2 here, I can also use the generic list to hold things of type integer. It becomes much more useful as a data type for me. Now let's continue on and see an example of modifying this list class further. We've just seen the generic list. Now let's look at this doubly linked list, which I've also already coded. And what I'd like to show in this is that my node that is here in my private class node not only has data and next of this generic type T, but now I've added this new property of the node to have a previous. So you can think of the node as having a next pointer and a previous pointer to look at the next node in the list and the previous node in the list. This would be advantageous if I wanted to flip forward and backward inside of my data structure. So this is all I'm going to add here into the definition of the node. I'm also going to, in the constructor, add a third parameter to the constructor and then establish the previous pointer based on what the user passes in. I'm modifying the toString slightly just to give a different visual look, so it shows the arrow pointing backward to give us a visual indication that we have a forward and backward pointer here. And next I want to talk about the changes that we're going to have to implement inside of this code here. I want to skip over this information about active for now. We'll come back to this in a moment, but let's just go down here and look at the constructor. No changes there except this active. We'll come back to this in a moment. But let's look at the changes that have to be made to the insert and insert to end and delete. Now when I insert a new value, I'm still going to insert to the front, so I'm going to have to insert the value and then point next to the list head, but I'm going to indicate that this new node now has a previous pointer to null since it's at the beginning of the list and there's nothing ahead of it. And if I'm not inserting into an empty list, then I want to make the previous list head's previous point to this new node. So I'm saying take the first node that was the first node and make its previous pointer point to this new node. That's going to give me a back pointer to the front of the list to point to this new node I've just created, and then reset list head to point to this new node at the beginning, and that's going to insert this new node that I just created into the beginning there. If I insert to the end, I'm going to have to do a little bit more work here as well. If list head is equal to null, that means I'm inserting to the end where there's nothing in there to begin with, in which case I just set list head to be this new node that contains a value and there's nothing after and there's nothing before it. Otherwise, I'm going to do similar work to inserting to the front. I'm going to create a current that points to the list head. It's going to iterate all the way until it gets near the end, and then it's going to insert this new node with a value, and the next node coming off of this new node I create is going to be null, but I want to make sure that the new node points back. Its previous pointer should point to what used to be the last, but is now the second last node in the list. The toString is slightly modified as well. I'm going to start out by printing null and just do everything I had done before. So the only difference now is I'm going to preface saying that there's nothing to the previous of list head. Length is unchanged, nothing different there. Position of is unchanged, nothing there. Delete is a little bit more complicated, so let's take a moment to check this out and see what's going on. Obviously, if there's nothing in the list, I can still return and do no work. Otherwise, I need to look and see, hey, is this thing that I'm deleting still at the beginning of the list? In which case, I'll set list head to next and make previous point to null. So here's a new line of code that we had to add to make sure our previous is not pointing anywhere for that new node that's now the beginning of the node. Okay? And then I'm going to still have my while loop. I'm going to iterate across all of the nodes, and if I have a match, then I'm going to want to see, am I about to delete the last node? So if current next next is equal to null, that means I want to get rid of the last node, and that's easy enough to do just by saying current next is equal to null, so I'm wiping out that last node that was a match there. Otherwise, if I'm not deleting the last node, I'm in a situation where I'm deleting a node that's between two other nodes. So this might look a little bit complicated, but I want to set the current next next previous to be current. That's going to set the previous pointer of the node just beyond the one I'm deleting to point to where I'm currently at. And then I want to set current next to equal to current next next. Now this code was already here. There's nothing different there. What I've had to add and insert based on the doubly linked list is that the previous pointer that's coming out of the node just beyond the one I'm deleting needs to point to the current node that I'm at. And that's going to make sure that both my forward and my backward previous pointers are working properly and removing the node when I found one that I need to get rid of. So a little bit complicated. Draw this out on paper if it's confusing to you, or check out the textbook. They have a nice step-by-step graphic showing what's going on there. But once I've made these changes to hold the previous and the next, let's go in here into main. I'm going to comment out the code that we just ran a moment ago. And I want to run some new code here that's going to allow us to demonstrate our doubly linked list. So now I have this data3, which is a doubly linked list of type integer. And I'm just going to stick with integer here, but you could certainly use candy bars if you liked. And I'm going to display this doubly linked list, and then I'm going to insert the value 100, and then display it, and insert the value 109, and display it. I'm going to insert to end to show that that still works, and insert the value 130. And I'm just going to continue to do some insertions to see what the list looks like. Let's leave it at that for now, just to see that the insertion is working on all of these. And what we'll get here is null null, meaning there's nothing at the beginning and nothing at the end. If I insert the value 100, then you can see that I've got this node with pointers going in both directions that has the value 100. I'm going to insert 109, and then I'm going to insert 130 to the end. And then I'm going to delete the value 100. And you can see that the deletion occurs properly, and 100 comes out, and we're left with 109 that goes directly to 130. I'll then insert 200, and then 300, and 400. And that's going to give me this nice long linked list. And what I want to do now is show the real benefit, because up until now, what's the benefit of these forward and backward pointers? The linked list worked just fine before, so what's the real advantage of having these previous pointers? Well, let's imagine that I have an active pointer that is somewhere here in this list, and I want to be able to move it forward and backward, almost like a tape head or a read-write head, to say what's the active record at any given time. And I can move it both forward, deeper into the list, or I can move it backward and move closer and closer to list head. So let's go into the doubly linked list implementation and drill down into what I've added that we kind of skipped over a moment ago. I've added an active pointer, an active node, and I've got the ability to print it out, which is easy enough. It just says system out println active equals active, and since a node has a toString that's overridden, it will display what that node is. I've got set active first, which is a method that I've added that's just going to set active to be list head. I can set the active to be deeper in by using this active more, meaning advance it on. And so long as it's not null, then I'm just going to set active to active next. That just moves it deeper into the list. And I've got an active less method that so long as active is not null, it's going to move active to be equal to active previous. So this is going to allow me, using these methods, set active first is going to move it to the beginning, Active more is going to move it down the list, and active less is going to move it earlier in the list. So here in main, what I'll do is I'll set active first, and it will be at the beginning of the list. I'm going to then show where it is. I'm going to move it down by 2, calling active more, and display where active is every time. And then I'm going to say active less to demonstrate the real power of the doubly linked list by moving my active reference earlier. Let's run this, and you can see we have built up our linked list, doubly linked list, as we wanted to earlier. And what's new now is that active is 400. We get that because we've set active to be the beginning of the list, so it's pointing to this node that has the value 400. I then invoked active more, which is going to advance it to the next one, and I display that, and you can see that it's moved on to 300, which is the next one on our list. I call active more again, and it's going to move it down here to 200, and then I call active less, which is going to move it back in the list, earlier into the list, and print out that active is now marked at this 300. So you can imagine different uses of this doubly linked list, but the real benefit is that you can move not only deeper into the list, but you can move earlier into the list. That's the real advantage of having those back pointers, those previous pointers. All right, let's shift now and look at the last of the data structures that I want to discuss here, and that's this recursive list. Now, we have this internal node, whether it's our generic list or our doubly linked list, we have this private node class that's going to manage all of the data, and our list class itself maintains a list head that points to the first element in the list, and thereafter we have pointers moving down node to node to node. We can also define our list recursively without defining a node internally, a private node internally. Let's look at maintaining just a first value of type t. So I'm going to define this new recursive list class, and it's going to hold something of type t. So I have this notion of first, which is the data, and then I've got a list of type t that'll be the rest. It's a recursive definition of a list to say I have a value and then I have the rest of the values, and the rest of the values is also stored in this recursive list. So the implementation of this is slightly different, but we get the same results, where I can set my constructor and set these up to be null initially. I can have a new constructor here that's overloaded that sets the first to be f and the rest to be r if I wanted to do that. My insert looks a little bit different. I'm always inserting to the front here, so if first is null, that means I don't have a value yet. So easy enough, I just set first to be the to insert. Otherwise, if first is not null, then I'm going to create a new recursive list and set the value of what is first currently to be the new first of this new list, and what's currently rest to be the rest of that recursive list. This is getting me a new space, essentially, that I can add, so I can place what was at the beginning deeper into my list, and then wipe out what is now first to be this new value that's coming in, and then set the rest of this list to be the new temp that I just created. So this is essentially creating a new list and moving the first deeper into that list and embedding what was the list deeper into this new list that we just created. So a little bit simpler implementation than we had with insert, in that I'm creating and using the data structure, the power of this recursive data structures to pull off holding all this information. Delete here is also been modified, so if first is equal to null, that means there's nothing in the list and I have nothing to look for. Otherwise, and you'll notice that we have the recursion, so here's the delete function, and within the delete function, I'm calling the delete function. So let's look at how we might get there. If I have a match, if this thing that I'm trying to delete is a match, then I'm going to set rest to null, and look to see if rest is equal to null. That means that there's nothing left and I'm deleting the first and only value. Then I'm just going to wipe out what's already here. This thing that I wanted to delete becomes null. Otherwise, if rest is not equal to null, I've found a match, but there's something later on, I'm going to look at the rest of the list and pull out the first and bring it earlier into the list. And then I'm going to set the current rest to be rest of rest, or you can think of us as skipping over one node and wiping it out. Okay, so if I do find a match, I'm either deleting the only value or I'm deleting a value where there's other things beyond, and I need to update this here. Otherwise, if I don't have a match, and here's the real interesting part, and here's where the recursion comes in, I check to see, hey, is there anything left to look at? Because if rest is equal to null, I've reached the end of my list and there's no reason to continue down. But if rest is not equal to null, that means there's something else in the list, and I'm going to call the delete function on this toDelete value looking at the rest, looking deeper down into that linked list. The toString function hasn't been changed, that's the same. So what we have now is a slightly modified version of the list class where I'm leveraging recursion to pull this off and implement it. And you'll notice that the overall code is actually smaller than what we had before. Just to prove that everything is still working as we would expect it, I've got some code here that makes use of the recursive list. I'm just going to create a recursive list of integers, and then I'm going to insert the values 10, 50, 90, and then I'm going to delete the value 10 just to show the buildup of this list and then that we can delete it properly. So let's run this, and let me comment out what we already had just to not confuse things, to say I'm only running this code with the recursive list in it. And the output that we get is that initially the list is empty, and then I add 10, and then I add 50, and then I add 90, and then I want to delete the value 10. So the delete function is working and it's deleting that value 10 out of that. So the takeaway from this is that we can define our data structures in slightly different ways using the power of recursion to change the implementation, but the functionality is the same. And the overall message of this tutorial is that we can vastly improve our data structures to handle generically different data types, so that I can insert integers or I can insert candy bars. It doesn't matter. The data structure itself shouldn't concern itself with what is being held. And I can also extend my list to contain previous pointers to allow me to navigate deeper and earlier into the linked list. And finally, I can change the implementation altogether and leverage the power of recursion to pull off my data structure. And that'll do it for this tutorial on advanced data structures and generic list types.